In this video, we would like to discuss the solution of time-independent Schrodinger equation for a special case, that is the state potential. So what is the time-independent Schrodinger equation? So the original Schrodinger equation is this. So if we like, the solution would be psi xt. If we find some solution of this wave equation that is valid for all the time, that is for all the t, that is the solution of a time independent Schrodinger equation. So how do we solve a Schrodinger equation after all? So that is actually another part that we would like to discuss in some other video, but in short I would like to tell you that we can write this is a wave equation. This is one dimensional equation because there is only one spatial coordinate, that is x. So we can write it in terms of two other function. So the first function is the function of x and the second function is a function of t. So this method is called the method of separation of variable. So like we get, after solving this partial differential equation, we get to ordinary differential equation. First equation is of term is in terms of psi x, and we call that the time independent Schrodinger equation. After following few steps, we will get to this time independent Schrodinger equation, and now we will have to solve this equation for a special case, that is the state potential. So what is state potential? State potential is something like for a certain region of space the potential is 0 and it changes abruptly to another value, that is v0 here at some spatial axis. It is we have denoted it x equals 0 in this case. So the potential is Vx equals 0 for x less than equal 0 and Vx is v0 x greater than equal 0. There is one question arising, that why are we studying this state potential at all? Actually we don't find anything like state potential in real world, but still we are studying it because state potential is in very good approximation with some real cases. That I would like to note one thing, that if two electrodes are metallic electrodes are in vicinity with each other, like both the electrodes are at some different potential, for an electrode inside this metallic electrode, that electrons will be in constant potential for anywhere inside this electrode. When it goes out of this metallic electrode, it will feel a other potential. It will change very abruptly. It will be something like that. It will be in some constant potential, it will be changed like this to other potential. So if we keep on changing the distance between them, this slope will be changing, and if we keep on decreasing the distance, the slope will be increasing and tending towards 90 degrees. So it will reach at certain point, it will be very good approximation with state potential. This will be some other value, and we are considering the lower value to be 0. It can be anything actually, but for v equals 0, it is the simple case, and another we have considered this equals x equals 0 because it is again give us the liberty to solve some equations. Means it is like for mathematical convenience we are considering all these things. Again there are two possibilities, that the energy of a wave or a particle, actually it can be both, because in quantum mechanics a particle can behave in like a particle or a wave. So it is some other entity that acts like a wave or a particle in some special cases. So whatever that entity is, let the energy of the total energy of the entity be E. So in this case we are considering its energy to be somewhere in between. So energy is less than V naught. So energy is less than step height. So we would like to solve this time independent Schrodinger equation for this special case. And one more thing, why are we considering time independent Schrodinger equation at all for this case? The reason is that V naught Vx equals V naught is constant for all the time. So at all t the potential will be V naught, and for this region potential will be 0 for all the t. So we can go for time independent Schrodinger equation. For going to time dependent Schrodinger equation, from time independent Schrodinger equation we will just have to multiply with some factor, that is phi of t. That is some other story, but first of all we would like to solve the time independent Schrodinger equation. Again there are two cases, that is first one is x less than equals 0. For that the potential is Vx is 0, so we get this equation, time independent Schrodinger equation. Now we have to solve it. So one more thing, that what does this Vx signify? Vx signify the potential in some region. So what is minus of Vx dx? This is the force. So in case Vx is constant, in this case Vx is 0, the force, this is equals to force, the force will be 0. So in this case the particle will feel no force, so that particle is a free particle. The solution for a free particle is that we can write in Euler's form is that x minus omega t plus I sine kx minus. How do we have got to this actually? We can actually consider for a free particle there will be no force. So it's like we have found that h bar k is p from de Broglie postulates, and h bar omega is energy. These two equations are here. For a free particle there will be no change in momentum, so p is constant. For p is constant we will get h bar is always constant, h bar is by twice pi, so k is constant here. Again energy is constant, for that will give omega equals constant. For a potential for a region where the potential is constant, we get the equation like this. In fact we actually for deriving Schrodinger equation we consider the equation of a free particle to be this, and we just consider some other like de Broglie relation, Einstein-de Broglie relations, and we consider some energy relation to get to the Schrodinger equation. So we can just now for assume the solution to be this. Actually we can now for that like we will considering this part actually, because for this representation the mathematical solution becomes much more easier now. And if we substitute this equation, this solution to this time independent Schrodinger equation, we will see that this perfectly satisfy the equation with, you can do it yourself. We will write it k1 here. And one more thing, this is a ordinary differential equation of second order, so there should be two arbitrary constant in the solution, because like for solving this equation there will be it will be integrated for 2 times, so there will be 2 integration constant which will give 2 arbitrary constants. So first arbitrary constant is e to the power I kx minus omega t. So we can assume that, so this is the, it's a wave traveling in the positive x direction, so x is increasing here. But you can see that here the k is in a root over term, so for k1 is in root over term, so if we substitute it in here, the k will be in the square term. So you can do it yourself, that you double differentially it, so there will be a k square term. So k is a square term, so here for k the sign is immaterial, so we can find that e to the power I minus kx minus omega, it is also a solution. We can write another arbitrary constant here, so it is the final solution. Wait, one more thing, we are considering the time independent Schrodinger equation only. So like for this part will be go to psi of t actually, so we can for now neglect this term. Actually for now we should have to verify this whether this is a solution to time independent Schrodinger equation or not. For that you will have to substitute it in this equation, and you will find that it perfectly matches the solution, which k1 equals to me h bar. Now we would like to solve the time independent Schrodinger equation for the region x greater than equals 0. So we would like to see classically how e to a particle would have behaved in this region. So in classical mechanics, the total energy is p square by twice m plus v, that is the potential energy. But in this case the potential energy, the total energy is less than the potential energy, so we would have got p square by twice m less than equals 0. So that would have given p to be an imaginary, so it is impossible. So in according to classical mechanics, we would not have found any particle in this region. Actually what would have happened that like if we consider there is a little it is the slope is not perfectly 90 degree, so that would be like there will be a force minus dvx dx. So as vx like as this slope tends to 90 degree, that slope will be very much, it will go to infinity, and but this force acts on the particle for a very short period of time, so the impulse is like finite. So that force is like tends to infinity, so this infinite, that is means huge force actually acts on a particle that goes to this region, but its energy is not sufficient to overcome that region. So this force like just perfectly reverses direction with this momentum. Just momentum is same as the initial momentum, but it just reverses its directions. So it is impossible to find a particle in this region. But in quantum mechanics, if we solve this equation for this region here, Vx is V0, so we will get that there is a solution exists in this region. So that's why it is possible to find a wave function or a particle or whatever that entity is in this region, that is classically excluded region. So we would like to consider the solution of this Schrodinger wave equation in this region. So like here we would like to assume the solution to be a kind of minus k2x, because there should be like the particle is not having energy, sufficient energy to move in this region, so we should not expect some kind of oscillating behavior like we had already found in this region. So it should be like this behavior should be like it just approaches x-axis, because it doesn't have enough energy for oscillating behavior or anything else. So we have just assumed this solution. Now let's see what happens if we substitute this in the wave equation. Like in the left hand side, it will be minus a square by twice m. Now double differentiating it, k square equals e to the power minus k2 x plus there is v naught psi x is e to the power minus k2 x. In the right hand side, there will be e term here and k2x. So if we equate these two equations, we will see that e to the power minus k2x is a solution for 2mv minus. So we have verified that this is a solution to the wave equation. Like there should be exist another wave equations like solutions, so that there should be two arbitrary constants. In the same way, it was the decreasing in the positive x-axis, it should be there should be another wave going in the other direction. We can just verify it again because there is a k square term, so time sign is again immaterial here. So the solution should be something like c there minus k2x plus t to the power k2x. So the final solution should be something like this. We would like to now see whether this is actually a eigenfunction. We would like to see whether this is satisfying the condition for the eigenfunction or not. The first of it is that it should be finite. We would like to see that for this solution, this term is going to infinity as x goes to infinity, so this term should not exist. So single Fibonacci is already being satisfied with all the terms. So I would like to see the continuity of psi x and first order derivative of psi x. It is continuous everywhere instead of x equals 0. We would like to see whether it is still continuous at x equals 0 or not. For that, I would like to see all these things. Like I'm writing the equation. So these two eigenfunctions should be equal at x equals 0. Now putting x equals 0, it will give a plus b equals d. Now finding the first order derivative with respect to x, and now equating at x equals 0, we will get. Now after finding the first order derivative of every term, now putting x equals 0 again, we get I k1 a minus b minus k2t. So we get these two equations. Now from these equations, there are two equations have three arbitrary constants. So now we are expressing a and b in terms of these. So solving these two equations will give a and b as after solving those two equations, we get a and b just like this in terms of this. So the final eigenfunctions or the solution of time independent Schrodinger equation will be something like this. So there is still arbitrary constant d left here, but this d determines the amplitude here, but the existence of d in the solution is necessary because d or any arbitrary constant in the solution is necessary because solution of time independent Schrodinger equation psi x is linear, so there should be always a arbitrary constant d in the solution. So I would like to make some predictions using this solution. So in that solution, d will come, in the prediction d will come both in the numerator and denominator. So d is actually immaterial. So first of all, I would like to predict the probability of a particle to be reflected at x equals 0. So for a classical wave, your reflection coefficient would have been just the ratio of amplitude. But in the case of quantum mechanics, the probability of reflection doesn't even depend on the amplitudes, but it depends on the intensity. Intensity in the other sense is the probability of finding that particle. So the probability of finding that particle, like probability of finding a particle B, that means like probability of finding a particle that is going in that direction. This is the probability of finding, or the intensity of a particle that is going in opposite direction. So we should consider this term only. Like in quantum mechanics, this is the probability function. So after writing everything, we will find that R is 1, so it is always reflected. Even the classical mechanics predicts the same result, that the particle has, as I've already discussed, the particle has lower energy than the step height, so it should always reflected by the extensive for his experiences here. So one more thing, like it is the same as the classical mechanics, but we would like to focus on what was not possible in classical mechanics, but what is happening here in quantum mechanics. That is, as for for the region x greater than equals 0, if we see the probability density of the particle, you will see that there is we'll see a term like this. For the probability density is strictly decreasing, exponentially decreasing for x greater than equals 0, but still there is a finite probability of finding the particle is there in that region. So it was not possible in the classical mechanics, but it is happening here. It is actually of great consequence of this quantum mechanics. One more thing we'd like to discuss here, that if it is possible to find a particle in that region, why don't we actually in macroscopic world don't find that particle in that region? So there is one other term, that is penetration distance. So penetration distance is from some more calculation we'll find del x is 1 upon k, k2 here. So it is as we had calculated before, this v0. So for macroscopic world, that m0 term is very much higher, so we get this term tends to 0, so it goes immeasurably very low, so we don't actually find any particle in the region. But for microscopic world, we do find if wave function in that region, that is called the penetration of the classically excluded region. So one more thing we'd like to discuss here, that the wave function for x less than equals 0 was d by 2 1 plus I k2 by k1 to the power I k1 x minus I k2 k1 to the power minus I k1 x. So it was a wave function. If we use the Euler's representation, that is e I theta is equal to cos theta plus I sin theta, if we use this representation here, we will find that the wave function is actually d cos I k1 x minus d k2 by k1. You can solve it sin k1 x for x less than equals 0. So what is the behavior of this function? If you multiply it by psi t, that is e to the power minus I e t by is where we will find that the nodes of the wave is not actually moving at any t, so the nodes are always constant. So what is it actually? It is a standing wave. So if we draw the probability function for this region, we will find something like this. This is x equals 0, so there should be nodes, so those nodes will be constant for all the time. So whenever we multiply it by phi t, we will get the whole solution of the Schrodinger equation, that is time dependent. but even after multiplying it by this term, the nose will not change its position. So this is a probability function, so there is no probability of finding some particle here, so there is a maximum amplitude of finding the particle here. So what is the behavior of this function when it goes to x greater than 0? So we have find that it depends on this or d kx, so it decays exponentially, so it should be something like this. When m goes higher and higher, this will be goes low and low. So this is the full solution of and some consequence of time independent Schrodinger equation for a step function and for energy that's less than the